in order for it to be good enough. And good enough depends on the particular application, right? So suppose we need the error to be less than 0.01. So here comes another follow-up question. How many rectangles?
So you just set it up and then...
Yup. How many rectangles are needed so that, for this same problem, the maximum error is, which I will abbreviate as the difference between the true integral and L30. That's what I defined the max error to be that. That this is less than 0.01. Using 30 subintervals, I got that the error was plus or minus 2.5 at most. Using these techniques, how many subintervals are required so that I can be sure that the error is, our answer is off by at most 100?
Yeah, what's I?
I is just the interval itself. Just basically, how many intervals, how many subintervals so that the error is less than 0.01? The max error.
That has to be greater than 7.
It's
Yep.
like 50 times 6 times 25.
That's crazy. That's a lot of
Yeah. So,
7,500.
yup, good. You guys are fast, right? Yeah. 6 over 2 times the width of the interval is still 25. Basically, in place of 30, you just stick an n, and you're like, yo, when is this error going to be less than or equal to 1 over 100?
Let's try that on the calculators.
So that's 75 over n is, oh, that's what, it's like easy. So yeah, so n has to be greater than or equal to 7,500. Okay, that is terrible. It is terrible. What this means is that if I want to use LRAM only, and I need to be sure that my answer is good enough, then I need 7,500 subintervals. All right, does everyone got this all making sense? Okay, could we possibly do better?
probably.
How can we do better? We can use more efficient methods. Precisely. Chris says trapezoids. So the same logic of everything we've just done will now be used to try a more efficient method. I haven't proven to you that the trapezoid method is more efficient, but I'm about to do so right now. Okay, so intuitively speaking, the trapezoid rule is like better, because it just like looks better, right? But what, and this is kind of subtle, what now, when does the trapezoid rule do well, and when does the trapezoid rule do not well? That is a very vague question.
Oh, it depends how the second derivative, yes, concaveness, how curvy it is.
Concavity.
Yes.
Okay, first can someone, June, can you, or Maya? Maya, what kinds of functions does the trapezoid rule nail perfectly?
The trapezoid, when it's like a line.
Yes. Maya says, dude, if you give me a linear function, the trapezoid rule is perfect. Does everyone appreciate that? Because now, what does the trapezoid rule?
Accuracy.
What does the trapezoid rule do? It just splits it up into subintervals. It goes over here, and it makes.
Well, you could use even one interval, and it would
In
be
that
right.
case,
Yes.
you just literally just multiply it.
Yes, you are exactly correct. Yep. Okay, but that's good to know. Okay, so when does the trapezoid rule go wrong?
When it's really like concave down or concave up.
Yeah, like when it's really concave, it's bad. So I think it's good to sort of qualitatively understand this. Suppose I was going to look at some functions which were very concave, which had a lot of concavity. So, and suppose I was going to estimate this interval with one subinterval. Okay? If I'm going to estimate this with one subinterval, then the trapezoid rule tells me that this is the amount of area under that curve, right? But suppose that the true function looks like, or something like that. Then there's going to be a lot of error because the true function is like this purple stuff. Following? Okay. But alternatively, if you have a different function on the interval AB with the same starting and ending points, then again using one subinterval, which is ridiculous, the trapezoid rule is going to say that's the area under the curve. But if the function is not so concave, then you're going to get error, but it's going to be like it's going to be less error. Yes.
Could we do a method that takes the beginning curve, the beginning slope as well as the beginning rate of change of the slope, and then use that?
But I think that the trapezoid rule, it's sort of built into the trapezoid rule that it's taking into account the slope.
No,
Because
I mean like curvy
Wait.
zoids.
Curvinoids?
Stuff
Yeah.
that would
Oh,
do
yeah, we
well
can,
with.
Yeah, we can. Okay, so for our analysis of the trapezoid rule error bound, what we are going to do is we're going to put a cap on the second derivative. Okay, so let's just begin. Suppose that the second derivative is guaranteed to be less than or equal to k2 on the interval AB. So let k2 be end upper bound on the second derivative. Okay. What kind of behavior will produce the most error? When are things going to go the most wrong?
When the second derivative is really
Equals
big
K2.
or really small.
Well, that's true, but I've now put a cap on the second derivative. This is a little bit subtle, right? Because what I'm saying is, on the assumption that my second derivative is never bigger than k2.
So when the second derivative is k2, it's the worst.
Yes.
Yeah.
Does everyone get that? It's kind of subtle and it's hard to explain. But if big second derivatives are bad, then if I'm capping the second derivative at k2, then the worst possible function is the one whose second derivative is k2 the entire time.
Wait, that's.
Okay? So yeah, so the worst function, and by worst I mean the function which will produce the most error, is the one in which the second derivative just is k2. Okay. So if the rate of change is less than boom, 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 boom. Good. Okay. So let's talk about this function, which is increasing at whose rate of change is k2. What does this function look like? Well, we can anti-differentiate. What is f prime?
It's like a
K2x.
K2.
Oh,
yeah,
no,
it's like
it's
k2x like
quadratic.
plus c or something, right? Yeah, and then something like that. And then, so therefore, what does the function look like? Anti-differentiate one more time.
K2 over 2 x squared
K2 over 2x squared
plus
plus cx.
Yeah.
Sorry. Plus cx
plus d.
Plus purple.
plus d. Okay.
Squared.
So,
Right,
this,
grab the square.
Wait, the x is squared.
this is the function. This is a generic function whose second derivative is constantly k2. So this is the function we have to fear the most, given that we have put this particular cap on the second derivative. Has everyone got that? Okay, so the picture kind of looks like this. And it is easier algebraically if instead of considering the ith subinterval, we just move it all the way over to 0. So I'll even just write that. It is easier algebraically to consider the interval from 0 to h instead of the interval from x of I minus 1 to x of I. The logic is still the same, but okay. So what is h? H is just delta x. So let's temporarily use little h to refer to delta x. And what I want to do is I want to look at the error on the ith subinterval. Okay. So here is h. Here is 0. And let's say that this is, oh, I did this already. Okay, so we have our function. So let's call this function q, this worst offender function. So f
Tyler, we saw
f is the actual function.
You took it.
F is the actual function. Q is the worst function. So what we've seen is that q is the function. We just did it over there. Q is the function which is k2 over 2x squared plus cx plus d. Okay. Well, built into the use of the trapezoid rule is the fact that we sample the function at the left endpoint of the subinterval and the right endpoint of the subinterval. That's our reality check. So when I am using the trapezoid rule and pretending that the function looks like this, and this green area is the area that I estimate is under the curve on this particular subinterval. Okay, but what does the actual function look like on this subinterval? Who knows? Okay, but given the assumption that the second derivative is less than or equal to k2, the worst function kind of looks like that. So this blue thing is this function that we call q. All right, so if I want to find, and the bell's about to ring, but if I want to find the maximum error on the ith subinterval, what do I need to do? I need to, the error, says Everest, is going to be here. The error, the maximum error on the ith subinterval is the difference between the error as calculated, or the area of the trapezoid, minus the area under this q function, which we can get via integration.
Yeah.
I'm going to finish this up on this video. It's going to be like 5 more minutes.
I was thinking of a function that take the line on the interval based on the derivative
Oh,
of.
wait,
Is that something like?
I'm just going to let this video, oh no, I can't let this video keep running. No, I'm just going to let it keep running for another minute. So this is f of 0.
It used to be like real tight.
Yeah.
And
She was
this
telling me
up
how
here
like one of her best
is
friends on
f
Snapchat,
of
her
8.
user Snapchat her so much.
Oh no.
But
not
you're still talking to a camera even though my class is leaving. It's really weird. But it's also true that this is the same thing as q of 0.
Shut.
Because the very basis of the q function is that
Hi, friends that I don't have.
it matches up with the. Are you saying hi to people? Just stop the video. This is kind of stupid.
Probably.
Yeah, just stop.
Bye, everyone.
The left point is just the same as lower m. It's
Okay, to be completed.
No
but
pops.
the slope of the subinterval.
Amateurish.